Then what we have is building on from that. We have these ideas of, sorry, my computer's struggling a little bit. Doing the recordings, my computer starts to sound like a helicopter and can lag a little bit. I do apologize for that. We have biofuels versus fossil fuels. Again, I'm using the same colors because biofuels, as you expect, are renewable. Fossil fuels, as you should also expect, are non-renewable. So biofuels are fuels derived from living matter. I've got those two. Well, yeah. I got those two mixed up. Yeah. They are the wrong way around. Whoops, I've copied the wrong. I put the wrong text box in the wrong spot. I do apologize for that. They're the wrong way around. Biofuels are derived from plant matter. Fossil fuels are derived from living matter compressed underground for millions of years. I've mixed those two up. I do apologize for that. But essentially, biofuels, plant matter, are produced at the same rate we consume it. Therefore, they are renewable. Fossil fuels are produced over millions of years and essentially, therefore, are really hard to reproduce. I really hope I haven't, therefore, given the wrong... Have I done the wrong one down here? No, I haven't. Good. I was going to say, why did I mix those two up? Biofuels are biogas, bioethanol, biodiesel. It makes sense if they have bio in front of them. It's going to be bio. Fossil fuels, they're like natural gases, coals, petrols, etc. And so also really important to sort of understand that's how that works. So we're going to go through the three main forms of biofuel now. This is very brief what I'm giving you. There is a much greater proportion of content that you need to go through for these. It's way more in detail. It's not even just much more in detail. It's way more in detail. But I'm going to give you a very brief sort of understanding of each of them. So you have biogas. So this is produced by anaerobic fermentation of plant waste. Now we are going to talk about anaerobic fermentation in a second, so please don't stress. We'll actually not in a second. We'll do it in the natural cycle. So it's probably a little bit away, but that's okay. And what's really important is that it's the weird thing about it is it produces the exact same fuel as natural gas, which is what we get as our fossil fuel version of biogas. So it's essentially the fossil fuel gas that we get. We call it natural gas, but it's not bio. So natural gas is a bit of a misnomer. However, what's really important about it is that it produces only about 32% methane, whereas our natural gas produces a much higher proportion. I don't remember the exact percentage, and you don't need to know the exact percentage, but the exact percentage is much larger. Therefore, when you take that gas, we don't really have a way to cleanse that gas in a sense. We don't have a way to get rid of the other gases. Like we have some ways of getting rid of some parts. We can't get rid of it all. So in the end, we're left with, a fuel gas that only is about 32% fuel. So therefore, it has much less energy. Therefore, when you're burning the same volume of that, that fuel, there's only 32% of it that ends up being fuel. Therefore, when you have a full volume of it and the same volume of natural gas, which let's just say, for example, is 70% methane, which is the fuel, this is going to produce a lot more energy than our biogas, which is one of our downfalls of it. But it is produced very renewably. It's produced from sewage treatment plants and landfill in Australia. We put in anaerobic bacteria and we end up producing gas by methane, which looks like this here. And these sort of little setups are how they work. And then we have bioethanol. Now, bioethanol, that arrow's not meant to be there, but it is. Whoops, why'd that go too far? Now, bioethanol is produced by anaerobic fermentation of glucose via yeast. Again, something we're going to talk about. So we will talk about this whole anaerobic fermentation and all of that. Bioethanol must be distilled prior to use. Now, you will learn about distilling throughout this topic. We won't discuss it today, but you will learn about it throughout this topic. But you'll also learn about it in Unit 4, Area Study 2. So you do need to know it in both. It involves boiling points for the products through large tubes, and then it allows the water to remove in one area and the ethanol to be removed in another. So it sort of purizes our bioethanol. As you can see here, this is what bioethanol looks like, and you'll find that bioethanol is in our E10 fuel. So I'm sure you've been to a petrol station before with your parents, or if you're 18 by yourself, and you've seen that there's this E10 fuel, which is a couple of cents cheaper than normal petrol. The reason it's a couple of cents cheaper is that bioethanol doesn't produce as much energy as petrodiesel. Petrodiesel produces a far greater proportion. But when the fuel is only 10% bioethanol, you still get nearly the same amount. You just get a little bit less. But essentially that bioethanol makes that E10 fuel slightly more renewable in a sense, because you're sort of subsidizing your fuel down a bit by putting some bioethanol in there. Some states like to refer to it as 94. So you know how unleaded we call 91? It means there's 91% fuel or 91% pure fuel. That means there are some, other bits in there. It's not as pure. When we put bioethanol in there, we treat bioethanol as another pure product. So we say it's about a 94. 95 is when you have, 95% of pure fuel, and 98 is your more, it's better for your engine to use a higher grade because it's more clean. There's less byproducts, there's less other things in there. However, some cars are actually not built to be able to take something that pure. They're built around the idea that the fuel is not all that pure. So that's why you can't go and put 98 fuel into a car that's meant to take 91. Although you can, and it wouldn't be the end of the world. Your car wouldn't explode. If you kept doing it, it would be bad for your car. Same if you go the other way around. A car that's built and requires 98, so a lot of these luxury car brands, they require that higher percentage. They don't have the capabilities to get rid of all of the byproducts of 91. You could put 91 in there once and it would probably be fine. It's not great for it, but if you continue to put it in there, again, it'll be detrimental to the car. So that's the idea behind bioethanol. And then we have biodiesel. Now, biodiesel is our closest comparator to petrodiesel. Now, biodiesel is produced by using plant oils or animal fat, so we get triglycerides, and then we do a transesterification reaction. Now, that is a big aspect of Unit 4 Area Study 1. You do not need to know it in detail at the moment. You just need to know the wording. You need to know that you get a triglyceride, you get a methanol. Now, that methanol should be produced renewably. You don't need to know how or where you're getting it from, but you should be producing that renewably, and you need to mention that. You don't want to be using a fossil fuel methanol, otherwise it's no longer a biodiesel. You've just used a fossil fuel. You then do a reaction, and what's left is you get glycerol. Now, glycerol is a bit useless. We don't want it. It's just a byproduct, but it's not detrimental to anything, so we just remove it and deal with it appropriately. And then we have biodiesel. Now, biodiesel is what we want. So biodiesel is polar compared to petrol or petrodiesel, and these both have a very similar energy content. But petrol being non-polar means that it has less intermolecular bonds. Something I said you should remember, you should know the strengths. It doesn't have hydrogen bonds, it doesn't have dipole, it just has dispersion. By having just dispersion, it's less likely to absorb energy and water. So I said hygroscopicity there, and I said absorption of energy. What I meant is sort of the fuel absorbs water, and then that water in turn, when you combust the fuel, will absorb energy. So when your biodiesel here, which I'm talking about, produces, when your biodiesel is combusted and it has a greater viscosity, it's thicker because of those stronger intermolecular bonds, because it has hydrogen bonds, because it's got oxygens and hydrogens, and because it's got dipole, because it has a polar aspect, and it's more hygroscopic. What that means is that it actually absorbs more water. That's what hygroscopicity means. It actually means it absorbs water. But I like to think of it as it absorbs energy. What that means is that that water, when it's in with that fuel, when you combust the fuel, the heat is meant to, move the pistons and so forth and get the car moving. If there's more water in there, it actually needs to heat the water first. And so therefore the water absorbs some of the energy as it heats, and therefore you don't get as much energy going straight to the pistons. So that's why it's a bad thing to be more hygroscopic. And biodiesel is more hygroscopic and more viscous, which means it's thicker, which means it doesn't flow as well. So when you get really cold, it doesn't flow at all. It's not useful compared to your petrodiesel or petrol. Now, this is what a transesterification reaction looks like. Please don't stress about it too much, especially at the Unit 3 Area Study 1 level. Your teacher may want you to know it for the SAC. They may say, look, we're going to go through it, we're going to learn it now. So please, therefore, then go and learn it and, spend some time on it. But a lot of teachers will say, oh, look, don't stress about it too much. We're going to go through it in a lot more detail in Unit 4 Area Study 1. So just know the brief, wording of it. you'll learn how to actually do it in this sense, like this diagram here, as you move through. Now let's look at our fossil fuels. So first of all, we'll start with coal. Coal, most common one because we use it so much in Australia. We sit on a coal gold mine, if you like to think of it like that, which isn't really exactly a good thing. Coal is a combustible black or brown rock. It's composed pretty much primarily of carbons. It's the largest source of energy worldwide because it produces electricity. And you really need to know this transformation process. So I like to think of it in terms of like a factory. You can search it up and find like factory sort of diagrams that help you sort of get your head around it. Essentially what you do is you get your coal, and your coal has carbons in it, and it has energy in a chemical form. It's locked within its bonds. You then combust the coal, so you heat up the coal, and the coal produces thermal energy. So as those bonds break, and as the coal sort of breaks down, it releases energy, and that energy is released as heat. And usually what it does is it heats up water. So it heats up a barrel of water, and that barrel of water heats up and boils, so it just continues to boil it, and produces steam. So essentially you've converted the energy from chemical to thermal in the coal to then thermal in the water, which is steam. And then that steam moves a turbine. So that steam moves up and it moves the turbine. And as that turbine moves, this becomes mechanical energy. So you've moved the energy from chemical to thermal to another version of thermal to now mechanical. As that mechanical turbine moves, it uses a bit of physics, it uses a bit of Coyle laws, and essentially what it does is it produces electricity. And so therefore you've had 1, 2, 3, you've had 4 energy conversions to get to electricity. Is that good? No, it isn't. 4 energy conversions, even if they all run at 80%, essentially you need to multiply those together. So the rule with energy conversions, which I'm going to grab my calculator out now, is if I want to do it, I would go 0.8, because that's 80%, and I would multiply it by 0.8. That's 0.8 here, plus times by 0.8 here. I'm going to times it by another 0.8, put it here, and I'll times by another 0.8 over here. Now that was 80% efficient. 80% efficient is pretty good. That comes out at about 40% efficiency. I hope you can see that there, but it comes out at 0.4096, so about 41% efficiency. That's terrible. And these are not 80%. These are usually a little bit less than that. So you can guarantee that the energy you're getting out of this is nowhere near what you started with. So that is why this whole process of using coal is flawed. It's a flawed process that people are, quite frustrated by in this aspect. There's also this concept here as well about peat, brown coal and black coal. So peat, brown coal, and black coal are just different aspects of carbon that have been, different aspects of coal that have been sort of sitting in the ground for different times. So peat has been there for less and isn't as deep down, so it hasn't been, pushed together and made into this, more pure version of coal, whereas brown and black start to get more pure and therefore have more energy per gram. And then we have natural gas and we have petrol or petrodiesel, whichever one you want to refer to it as. We like to refer to it as petrol now. It used to be more referred to as petrodiesel, but they're moving towards just petrol. Natural gas is a wide variety of hydrocarbon gases, so methane through to butane. You realize it's a fuel. You find in ground pockets, it's a lot higher percentage of fuel compared to biogas, and therefore that's why you get more energy. Petrol is the refined version of oil that is collected from large deposits under the ocean. So we get oil rigs under the ocean. What do they get? They get crude oil or petroleum, a bit of both, usually crude oil. They then refine the product into petrol, petrodiesel, and diesel. They're just different levels. They're just different lengths of carbon. Petrol is purely usually octane, so it's 8 carbons long, whereas diesel is usually all 16 to 18 carbon long molecules, and then petrodiesel is somewhere in the middle. The reason why petrodiesel is most common is it kind of has a lot of different ones kind of combined. Petrol is usually purely octane, or maybe a little bit of 9 carbon, but usually just 8. And then diesel is usually, again, a very small range of 16 to 18, whereas everything else in the middle is petrodiesel. Each of these collections, this here is the same length of hydrocarbons. We try to keep them the same. Sometimes there's a couple of different ones, as in diesel, and same with petrodiesel. Petrol, they try and keep pretty pure. They try and keep it mainly octane. And that's why each of these sort of release different amounts of energy. and they're refined through this process called fractional distillation, which you will learn about. It used to be a really big part of the study design. It's now just a smaller aspect, but you do need to know it. And it's something that we won't really cover today, but it's a version of refining our fuels.